So hello everyone. So welcome to our this week's Efficient AI Seminar talk. So today, we are glad we have the Professor Emre Neftci from the UC Irvine to give us a talk. And so here's the short introduction for the. So he received his master's degree in physics from the EPFL and his PhD in 2020 from the ETH. So currently he is an assistant professor in the Department of Cognitive Science and Computer Science at the University of California, Irvine. And his current research explores the bridges between the neuroscience and the learning, with a focus on the theoretical and the computational modeling of learning algorithms that are best suited to neuromorphic hardware and non-volume Neumann computing architectures. So let's welcome to his talk on the programming neuromorphic hardware for fast, efficient, and online learning.
Thank you both for the introduction and also for the invitation to this seminar. So it's going to be my pleasure to talk about some of the work that we're doing that relates to how we can build perhaps more efficient technologies should we take inspiration from neuroscience and the brain into consideration. Okay, so let me start with, let me start with this simple example of firstly why we should think about our brains and why they're cool. So this is an earlier study of Josh Tenenbaum at MIT, which made the point that we are very fast at learning. So in this case, if I tell you these three images in the red boxes are called tufas, they don't exist, they're just something. But I ask you to find all the other tufas in this picture, you'll have no problem in finding these, right? And this is a remarkable capability that we have, that just based on few samples, we can immediately learn what they are. You've now learned what a tufa is. And if you've already seen this paper before, well, you might already know what a tufa is, which is another remarkable capability that we have, is that we tend to remember things over a very long time period. These are things that conventional deep neural networks cannot do. Regardless of how they're implemented, there is a significant gap between what the brain can do in the speed of learning, but also in the amount of data it needs in order to generalize. Okay, so how cool would it be if we could implement these kinds of machines in hardware? Okay, so let me just take a quick dive into neuromorphic engineering. I've seen from previous talks at the seminar that there were talks on this topic, so I won't spend too much time on it. But I'd like to emphasize the fact that neuromorphic computing really strives to capture the computational processes on a physical substrate, and that physical substrate is something that we build based on inspiration from the brain. So, and the idea comes from early researchers at Caltech, who basically stated that because the constraints of our hardware, current hardware systems, technologies, in this case CMOS, are similar to those of the brain at some level, then the systems that we can build from the bottom up might have some resemblance to the brain. And this is the approach that Richard Feynman called the analysis by synthesis, but basically that if you can build a brain-like system from the bottom up and then analyze what you've built in order to understand, in this case, how the brain might work. And so the goals of neuromorphic engineering are both to understand the brain, so to provide into neuroscience, but also as a technology. Once we have built these systems, we can use them for, say, low power and data efficient learning. So why is the brain efficient? I mean, this is, of course, a very broad topic. I can't answer in a single slide, but just consider this, this fact here, that if we have two chips here, and each of them is composed of neurons. The neurons here are these kind of sticks. whose outputs, if we follow the brain's model, is going to be these sparse on or off events. These sparse events are written on a common bus, and so we typically use something called the address event representation, where we can write the address of the neuron that spiked, but time represents itself. And basically when you receive the spike is when that spike occurs. So we don't need to include any timestamp here. Then these events get decoded on the receiving side into spikes, which then impinge on these synapses, which contribute to the spiking of these neurons. So the hallmark of this approach is that, well, only spike events are routed, as I said. So that's a very kind of efficient communication, means of communication. But there's also another interesting aspect, which is that a lot of the computation here occurs locally. So the neurons within themselves, the construct, the cells or the circuits can be very complex with analog computation, but the communication is this very simple digital event. So it's very scalable, but it's challenging to use, right? So how can you implement, say, machine learning on these kinds of, on this kind of substrate? In some ways, the issues that we're having, the problems that we're having are not so different from this compute in memory approach, where you're trying to bring as much of the computation as possible onto the memory. In fact, most of the challenges that we have are similar. So solving the problem in neuromorphic hardware might also actually help compute in memory technologies. Okay, so let me just give a quick ecosystem of neuromorphic computing and hardware with respect to software and hardware. So, but starting with an example that would be familiar with you, which would be machine learning. So, if you want, we have machine learning algorithms. We generally, we have software that allows us to conveniently implement these machine learning algorithms, which are then compiled into some general purpose hardware. Or in some cases, we even have machine learning accelerators that would directly take some of the parameters or your model bit file basically and run it efficiently on hardware. So now bringing this neuromorphic engineering, the brain inspiration into the picture here, what we have is that we take inspiration from neuroscience in order to, of course, traditionally to build software and hardware systems. For a long time, so meaning in the previous decade, most of the neuromorphic engineers have focused on taking directly neuroscience concepts and implementing them straight in hardware, somewhat bypassing a little bit the theoretical foundations that will allow that hardware to compute. It was an interesting approach just to get an understanding how we can build the hardware that's more brain-like, but it did lack somewhat success in or practical applications because it just didn't work that as well as machine learning accelerators or the machine learning in general because it wasn't based on a theory. So recently, in the last 3-4 years, there's been more and more links between neuroscience and machine learning. The idea of using machine learning algorithms as a foundation for understanding how the brain works, how it learns, is becoming more and more popular. We have some work on this, but also, the larger machine learning community has also been contributing to this field. So I'll be talking more about our work here. Before I go into this, I just want to say that the approach that I will be taking, I'll be talking about here, is one that really, instead of starting from neuroscience, it's really starting from machine learning. So what is the problem that we're trying to solve? How can we formalize this in terms of the dynamics that we know from neuroscience and those that we can implement in hardware or neuromorphic hardware? And this, I think, I've tried to convince you that this is the right approach for building kind of specialized technologies, neuromorphic technologies. Perhaps not necessarily for understanding the brain and building a large brain, although I think even in that case, we can still say something. Okay. So let me start with just the basics of our building blocks. Generally, neuromorphic hardware consists of these spiking neurons. I mentioned earlier that neurons communicate through address events. And so that is, and the internal dynamics of this analog behavior. Here's the simplest possible neuron that basically conveys some of the important features of spiking neurons. This is a discretized leaky integrated fire neuron. It's leaky because the state, which is the membrane potential at the time step t+1, is equal to the previous time step times some leaks of this beta factor is between 0 and 1, but closer to 1, some synaptic inputs, and maybe some, this term here accounts for the resetting of the neuron after it has spiked. The S is here, the output of the neuron, so think it as the result of applying an activation function. The activation function here is basically the step function, 0, 1 step function. So in this case, what the neuron would have, the internal state membrane potential would have this kind of behavior, and the neuron would spike and then get reset and so on. And this here would be the input. So what I'm going to do now is to take this neuron model and to decompose it into different time steps, basically unroll this model to make it to make a connection to more familiar machine learning and neural network concepts. So here we go. So we have, because our neuron has a state and time, we're going to have different basically nodes in this graph at different times for different time steps. And every arrow is basically going to say how that node is transformed into another variable, into another node. So we have here the U at t+1, so that feeds into the spike, and therefore you get an arrow that goes from U to S. Add here the leak, which basically connects the membrane potential in time. So that basically is the state, internal state of the neuron. The input events, they come from a state called S in and feed into U, and they eventually go to the next layers and so on. You can also imagine that you have recurrent connections. In fact, recurrent connections outnumber feed-forward connections, and they're in the brain. And so this is a really important feature as well. And so these correspond to arrows that go from the state back into the membrane potential. And so what we have here is a picture that if you just open any deep learning or neural networks book, you have the same graph as that of a recurrent neural network. So this is all of this is to say that a spiking neural network is nothing else than a particular type of recurrent neural network that operates at a much finer time scale with respect to the inputs, but otherwise is mathematically similar. And so what this means is that the tools that people use to train recurrent neural networks are also applicable here, with some caveats that I'll be talking about. But the overall picture is that, well, in the end, we can think of neuroscience and neuromorphic hardware or biological neural networks as being not so different from neural networks in some cases. So we can, instead of just plugging in some learning dynamics and some neuron dynamics, what we can really do is think about some objective function that we're trying to solve. It can be classification, it can be navigation and planning, or whatever you're interested in that can be written down as an objective function. The neuron model, well, basically that's what we've seen so far. That's the spiking neuron with its internal dynamics. And then the learning rule is just basically going to be the gradient descent of that objective function. So now the interesting thing that happened in the last years is that we realized that gradient descent is actually relatively compatible with what we know about synaptic plasticity in the brain, in the sense that the leading models of synaptic plasticity were called spike timing dependent plasticity, which was basically an update that depended on when the input spike and the input neuron and the output neuron spiked, the presynaptic and postsynaptic times. It turns out that the rules that you get by gradient descent generally on this type of neuron, on this neuron and objective functions, is something that has similar terms. So one which is going to reflect the error that the neuron is making. That's basically, if you think of it, the backpropagated error, assuming you're using gradient backprop. There's another term that basically the derivative of the activation function. That's the postsynaptic neuron. So basically, the something that reflects is reflected by the output neuron state, and these synaptic eligibilities, which is basically a trace of the inputs that comes into the neuron. These are called three-factor rules in computational neuroscience because they have these three factors. And it was the idea that we had this third factor, which is the error, which was kind of interesting. And the most interesting actually was that we can put these three elements together and perform almost exact gradient descent. Okay, so it's a mathematical framework that can really help us and not in building neuromorphic hardware. Okay, so I said earlier that there were some caveats, and I'll be talking about them now. And these were the reasons why, a couple of years ago, we couldn't even think of doing these gradient descents and synaptic plasticity. So here's the learning rule that we had earlier. So remember, this one was for error, this one was for postsynaptic derivative of the activation function. This first term here, that's easy to calculate. It's really like a trace of the inputs. It's fairly straightforward. These two terms pose a problem. The first one is that, well, if we have a step function, then this theta is going to be, it's not going to have any gradients, right? So it's basically going to be zero everywhere except infinity when u is equal to 0. So the first trick, which works really well, is to replace this theta with a differentiable nonlinearity, say a sigmoid or corrected tan h, or whatever you'd like, but only for the purposes of optimization. So when you do the forward pass, you still use these step functions, but when you go the backward pass, you trick the system to say, okay, so here calculate the gradients as if the activation function was one of these smooth functions. This works very well. We call this the surrogate gradient. Other people have different names for it. It's used routinely now for training neural networks. And the idea is really as if you're taking this rough loss function and replacing it with one that's smooth, which would kind of intuitively help that ball roll down the valley. So that's, I'd say, almost a solved problem. There are even better methods than surrogate gradients that are being developed out there. Another problem, which is much more serious, is the credit assignment problem. For one, the deep spatial credit assignment problem. So anytime you think of learning in physical substrate, you have to think of which information is local to the processes that are implementing the update, right? If your learning rule requires information that's not local to it, basically that information is placed on another chip or another neuron, you need a channel in order to to communicate that back to the neuron, and that costs a lot. And so the idea is to approximate this channel and to implement approximate learning rules and solve the spatial credit assignment problem. So before I get to the approximation, so in backpropagation, what you would do is just you would backpropagate the events, which actually induces a non-locality because you require these backward connections that are symmetric transposes of the forward ones. This is also called the weight transport problem. It turns out that there's one simplification you can make for this, which is to replace these backward weights with random ones instead of the ones that correspond to the symmetric transpose. That's called the feedback alignment approach, or its cousin, which is the direct feedback alignment that directly feeds back the errors from the top layer down to each individual layer. These approaches work pretty well, although they still have the caveats of layer-wise locking, if you're familiar with that. Plus, they do have a significant gap with respect to backpropagation, but they do overcome the weight transport problem. The approach that seems to be working the best and that we are also pursuing is to have these local loss functions or local errors. You define for every layer or groups of layers a loss function such that if it solves locally, that loss function is going to do a good job overall. Of course, it's not easy to define these loss functions, but just by trial and error, people have found that if you just use classifiers instead of so layer-wise classifiers, that works pretty well on classification tasks. But there are also some more recent work in which people used contrastive losses, where the goal of the layer is to predict whether a particular sample is true or fake. That seems to perform even better, almost as good as backpropagation through the network. So this solves to some extent, although I would not say that's a completely solved problem, but we do have ways of performing spatial credit assignment without requiring non-local information and without backpropagating through the entire layer. And that's really nice for implementation, like real-time and neuromorphic hardware implementation. Another problem is that, so remember that basically our neurons are dynamical systems, they have a state and time. Well, this means that we also need to solve a temporal credit assignment problem. So not only in space, but also in time. And let me just take a quick detour here of how these problems are solved. So what I want to say here is that automatic differentiation, which we use routinely, has actually been a little bit the hidden figure of deep learning success. It allows us to define a network and just to take the gradient across the network without worrying too much of what went inside. Right? As a user, this almost seems like magic once we do this loss backward. So all the gradients are computed. I mean, pre TensorFlow or Theano times, this was very difficult to imagine. It turns out that this is automatic differentiation was something that was used in the scientific computing community for a very long time. It was only later taken by neural networks community. And so within what people do in the scientific computing community is actually a couple of interesting things that we can learn in order to solve this temporal credit assignment problem I just mentioned earlier. And let me give you a quick idea of what those are. So let's assume that we'd like to, just as we had before, we'd like to take the gradient of some loss function L with respect to the parameters theta, right? So by the chain rule of derivatives, you'll get these bunch of Jacobians here. Backpropagation consists of basically multiplying these Jacobian matrices, although we never actually generate the whole matrix, but we do this vector by vector. We start from the left and then we go from the right? So we calculate this Jacobian and multiply it with this one and so on. There's no reason that we would have to go from left to right. In fact, we can also go in the reverse mode, which is actually counterintuitively here is called the forward mode, where we start with the first Jacobian and go back to the first one. Now, the point I'd like to make here, actually 2 points. One is that there is significant flexibility in the computation of gradients. Backpropagation is not the only way of calculating the gradients. We just have to basically multiply these matrices together. So you can imagine that it's like we can place parentheses in this expression in any way that we like in order to solve our problem more efficiently. The other point I'd like to make here is just comes from the math here, is that in most cases for neural networks, the reverse mode, so backpropagation, is much more efficient in terms of memory and computation. But the forward mode has the advantage that a lot of the information that we need is actually going to be local to the learning world. Okay, so I'm going to come back to my story of spiking neurons. So now you know that there's reverse mode and forward mode computation. By the way, the forward mode is sometimes also called real-time recurrent learning. And apply it to our spiking neural network graphs. So these are the same graphs that I had earlier. So with backpropagation through time, what happens is that we get some input. This gets propagated forward all the way to this loss function. And once we calculate the loss function, we can backpropagate the errors through the network. This is backpropagation through time. It's a straightforward application of this reverse mode automatic differentiation. What you see is that Well, this works relatively efficiently, but that the updates only come after a while. So in this case, after you've been able to calculate the loss function, you have to backpropagate through the network. This means that you have to retain the state of this entire graph in order to calculate the gradients, and that has a cost, a memory cost. In the forward mode, it's kind of magically you can really propagate all the information you need for calculating the gradients forward. Okay, so in this case, there is no backward pass. You do one pass forward along with the forward auto diff. And at the moment you hit this time step where you have this loss available, you can calculate these updates. And so the learning rule is and the name also refers to that, is that it's real time, it's online. Okay. The reason why we don't use forward AD is because it's much less efficient, as I mentioned. So it scales quadratically, the computation space scale quadratically and cubically, respectively. But it doesn't depend on time, all right, because it's every time step. Basically, you propagate forward, so you don't have to do a backward pass. So that is a reason why RTL, this forward AD, is not used in general in neural networks. But it has some advantages, which is, as I mentioned, it's online, but also it doesn't have this problem of the weight transport, because all the information goes forward. You never need to propagate things backwards, so you don't have this weight transport problem. Unfortunately, there's some aspects in this rule that makes it non-local. I'm not going to go into details there, but this is not a good candidate. It turns out that we can actually mix these two things. Just as we had forward mode and backward mode, remember, with these calculation product of matrices that we can do from left to right or from right to left. Well, what we can do is that we can actually mix those two modes. We can have forward mode in time and backward mode in space. And the advantage of doing this is just through a couple of approximations I'll be talking more about, elaborate more on later. We have a learning rule that has that doesn't depend on time anymore. It's online. It doesn't really require transposes unless you do need transposes in this spatial backward pass here, but you can use feedback alignment and so on. And so this makes it a local learning rule. Whether you have K or K squared is going to depend on your particular neural model. But most of the things that we do in that scale are scale as K. So it's an extremely efficient learning rule that does not depend on time, but still takes into account the full dynamics of the neuron. So it's an excellent candidate for implementation in hardware. Just to give a little bit more technicalities here, so once you take the gradients of this neural network, so you also end up with a product of Jacobians. So we take here, so this is a derivative of the internal state U with respect to their parameters, and we decompose that. And just as you have a recurrence in the forward pass, you also get a recurrence in the backward pass. And that recurrence is basically this G of t, which is this derivative, is equal to the H of t, which is how the state changes over time due to its internal dynamics. This is the previous state of the derivative, plus this additional term, which are the immediate Jacobians. That really corresponds to the calculation of d of u with respect to the parameters at that time step. Okay, we can decompose these this recurrent matrix into two parts, one which has the implicit connections and one which has implicit recurrences, explicit recurrences. Now think of these as implicit recurrence as the neuron feeding a state back to itself, and explicit recurrences as one neuron feeding its state, an output spike to another neuron. So across neurons or within neurons, respectively. So the mixed mode approach is really, if you can see the difference between these two slides, is rather than doing a full forward pass, we do a forward pass in time and a backward pass in space, as I said, but we also ignore these explicit recurrences in the calculation of the gradients. And this is what gives us this huge memory and time advantage in our algorithm. This does have a slight cost in accuracy, but as you'll see, in general, it's not that much of a big problem. Okay, so basically what I showed you here is a way of simplifying this learning rules. Actually, our method of ignoring these explicit recurrences is not the only approach. You can also simplify these matrices using lower order tensors and also something called the sparse n approximations, which would be somewhat of a generalization of our explicit recurrence ignoring in the case of sparse connection matrices. So the reason why things become more efficient if we ignore these explicit recurrences is, I think, made clear in this picture here. So this is just showing graphically those matrices for the implicit part and the explicit part here. And these immediate Jacobians, so these immediate Jacobians are just basically the derivative of your W times X with respect to W. So dark here means that there's a value that's non-zero, otherwise it's 0. So what you have here is that on the diagonal, you'll have non-zeros for these implicit recurrence, because this means that the neuron only affects itself. So it's not that this matrix is not going to have the contributions from other neurons. So that's diagonal. The explicit recurrences are going to be the exact opposite. So we're going to have only non-diagonal terms. Okay. The result of this is that if I multiply my states, which may be block diagonal like this, with a non-diagonal matrix, I'm going to get something that's potentially dense. Okay. Whereas whereas this one, because it's diagonal times block diagonal, my result is going to be block diagonal. So if we ignore these terms while calculating the gradients, we end up with a recurrence that only requires calculating these block diagonal terms. And that's where we gain a lot of the efficiency. We can ignore the computation of all these 0 terms out here. Okay, so basically this implicit recurrence preserves the block diagonal structure, whereas the explicit recurrence destroys it. I'll skip this one. So I want to say, so what's the consequence of ignoring those explicit recurrences? Well, here's a couple of experiments that my colleague Friedemann Zenke made. So these are trained spiking neural networks to solving some problems like mnist. These are spoken digits. These are also spoken digits, but not pre-processed. And these are the speech commands, the Google speech commands. And what you have to focus on here is the blue versus red. So blue is when you ignore these explicit recurrences, and red scalability if you do that. In some other cases like this one, this is called RANDMAN for random manifold. This was specially constructed with a delay, so you really need that memory. In that case, you do, in some cases, have this big loss. And that is somewhat expected, but it's not to be minimized either. It is problematic. Okay. So now putting all these elements together, so like, can we actually solve practical problems? Well, it turns out that we can, although not exactly in hardware for the moment, but I'll show you some examples that we do have running on hardware. So this is a gesture classification problem where the gesture is recorded with the DVS camera. So DVS camera is this cool camera that just produces events where a pixel has changed intensity. So the output, rather than being an image, is basically a cloud of events as you have here. And that cloud of events, basically, we're only feeding a couple of these events into the network, basically correspond to that time step. So it's a continuously operating network on these events. We apply this, so we send this into this convolutional spiking neural network. This was written in PyTorch, but it has all the spiking dynamics that I told you about. We use auto differentiation in order to calculate the gradients. In this case, we're using loss function, local loss functions, which actually every loss function is trying to reduce the classification error at that layer. without backpropagating further. And this performs very well. We need a slightly larger network compared to backprop through time. But in the end, because the rule is so efficient, we still end up being less computationally expensive than backprop through time. And so, and we get very good results on this. So all this learning is purely online and only requiring local information. So now, in order to get into more practical learning scenarios and moving more towards this idea of the tufa that I had in the beginning, remember these flowers that I told you to class to learn, or flower-like objects. It turns out that there's a challenge. So learning with real kind of streaming real-world data is really hard. You may, of course, know about the catastrophic forgetting problem, which is that if your data is presented is not identically independently distributed, then you will get catastrophic forgetting in that case. And that's kind of predicted by the statistical learning theory. In addition to this, we all know that deep learning requires a lot of data, right? So whereas I just, for the TUFA, on 3 examples, you were able to learn it. All of these problems are compounded by the fact that if you're running on a physical substrate, you can't just make multiple copies of that network and run like with a batch size larger than 1. So learning in a physical substrate is like learning on a batch size equals 1. And so already we need a lot of data, but if we also need to make the batch size equal to 1, that means it's going to be extremely slow. So what can we do? So for the first problem, for the catastrophic forgetting problem, well, we can have these more complex synapse models that, this is one example with this elastic weight consolidation that can compensate for the catastrophic forgetting by making the neurons less, changing their learning rate according to how well they represent previous tasks. Another approach is to make the data more IID by replaying previous data with the obvious, problems that might incur. Offline methods are also of interest, and I think I'm particularly interested in these, such as transfer learning. You can imagine that instead of learning on the spot on the hardware, you can learn offline with a given data set, and then transfer those parameters onto the hardware. So that would be and do a few steps of learning then on the at the edge. So that would be the idea of a transfer learning, and you can take that idea even further by optimizing the speed at which it would learn once you deploy it. So that would be meta-learning, or in this case, this is a picture for mammal, model agnostic meta-learning, where you can find a set of parameters and, from which you need just a few steps of updates in order to reach a good accuracy on the new task. And of course, federated learning, where multiple devices learn and transfer their parameters would be another approach. So what I'll be talking about, I'll be focusing here on the meta-learning and the transfer learning part. So we did this transfer learning on the Intel Loihi. So Intel Loihi is the hardware that's being developed at the Intel Neuromorphic Consortium there. The chip has 128,000 spiking neurons, but very interestingly, it has a programmable plasticity rule in there. The plasticity rule is pretty much like what I told you here. It can only operate based on local information, so based on presynaptic and postsynaptic states, and in some very limited sense, a global factor, which in this case could be, for example, error. And so we implemented this surrogate gradient learning rule that I told you about in this earlier in this talk into the chip, but we didn't want to do learning from tabula rasa for starting from 0 on the chip, and instead we pre-trained the network and transferred a network which is really a model of what's happening inside the Intel Loihi chip. We transferred those parameters and did just a few steps of learning on the chip. And we applied this again in this case of the gesture recognition. And my student here was basically teaching this network a new gesture. And even after a single shot, so a single presentation of that gesture, he was able to get, so basically on the testing task, basically 65% accuracy. So, and this is a 5-way task. So it's pretty remarkable just after one step that how much, at least for us, it was quite remarkable. We can take this further. So in this case, what we're doing, we're just training that last layer, and we're just really mapping these parameters, which weren't particularly optimized for fast learning. Oh, sorry, and yes, just want to say, this is here to say that this is similar to this idea of the tufa. So what we're doing now is to basically, instead of just doing transfer learning, we are meta training these parameters. Now, cool thing here is that this whole surrogate gradient approach is basically allows you to apply any learning rule that we, the machine learning community could be using. And in particular, this model agnostic meta learning, which I just mentioned before, it consists of two parts. One which is an outer loop that basically optimizes the update rule, and an inner loop, which is, as we just saw before, it's just basically one gradient update. So the outer loop optimizes through that gradient update rule. So the idea here is to have this outer loop occur in a supercomputer, or some large computer, along with the inner loop. But once you deploy, you only do the inner loop. Okay, this allows you to first find hyperparameters that work well, but also to find the parameters that after which, as we saw before, a little bit like we saw before, you just need a few samples to learn effectively. And if we have these spiking neurons here, we can use those surrogate gradients. So basically these smooth functions, which, and the auto differentiation doesn't care as long as you have a continuous derivative. It can take second derivatives, which is, by the way, what mammal needs. So the point is to make here that we can implement mammal with spiking neurons with no problem, although it is computationally expensive. We tried this on a special task that we've constructed for this purpose. There was a double mnist out there, and we constructed a double neuromorphic mnist, which basically took these mnist digits recorded by DVS camera and basically collated them onto another. So we have up to 100 different classes. But every task corresponds to classifying 5 different classes, 5 different pairs. So that's why it's a one-shot 5-way classification task. Some of this naming of meta learning requires getting used to, but it's basically not too different from what people have been doing with the omniglot and so on. And that's where we see basically, with the approach that we have with the spiking network works at about 98%. Which is very good. And this comparison actually with a conventional COMNet is not fair, because a conventional COMNet sees the entire image, whereas the spiking neural network only sees the last frame. And so it has less information available to it. And so just after one step, so at 0 steps, the network performs at chance. It's 5-way, so 80%. After one update, it performs already at 98%. So it was able to learn this classification just with one sample. And I'd like to, I'm almost done with the talk here. So I'd just like to make one comment here, which is really behind my excitement for this whole approach. This meta-learning, model agnostic meta-learning, in the inner loop only requires, you can have anything that you want, but it basically, the particular result works with stochastic gradient descent, so pure gradient descent, not Adam or whatever. So the learning rule there is extremely simple. And in addition to this, the learning rate is quite high. And you would expect it to be high because you want to learn after a single step, right? So if you want the network to change its behavior after a single update, then you need that learning rate to be high. And this, it turns out, for hardware implementation is actually really cool, because in hardware, memory is very costly, especially if the memory is close to the processing element. And it's certainly the case, for example, in that Intel Loihi chip. And so this means that if the learning rate is high, we don't need to worry too much about precision, right? So we can have low precision synapses where, making one update almost basically corresponds to flipping maybe 1 bit, but that has a large effect on the neuron. And so this overall approach, I think, has this really appealing aspect that maybe meta learning offline could simplify the task of learning online at the edge. In fact, there's some work not in the neuromorphic field that really shows that. And so I think this is a very exciting approach for building neuromorphic learning machines. Okay, so that's the end of my talk, and I'd like to just give a quick summary here. Is that now I've defined this kind of middle out approach where we started with machine learning tools, software tools, and using similar concepts to model dynamics of neuroscience. So training these spiking neural networks is it does remain slow, but we can still achieve good results, especially when we use this mixed modes approach. So I'd like to thank my collaborators here. So we have Friedemann Zenke, I did most of the surrogate gradient work with. Kenneth Stewart did the Intel Loihi work along with Garrick and Sumit, and Jack Kaiser and Hesham Mustafa worked on this multi-layer neural network we use for gesture classification and the funding. So thank you for your attention.
Thank you, Emre. Very excellent talk. So, any questions from the audience?
So I will ask actually 2 quick questions. Thanks, Emre, for the great presentation. It was very exciting, and I actually learned a lot from the talk. So I was just curious about the first question about the use of mixed mode that you mentioned. How like forward, backward in time and space helps, but you also mentioned it comes at the minor cost in accuracy.
Mm-hmm.
I was curious about like what's the root cause for that accuracy loss? Is the surrogate gradient, or there's anything else?
Oh, so it is exactly this one here. So if you look at, so here's the graph of that learning step. So normally you back propagate through the entire network. Now just imagine that the connections here are all orange, so you're back propagating through this network. In these approaches, you truncate the gradients here. Okay, so yeah. And that has, because you don't have the right gradients anymore, it has impact on accuracy. That's the main reason, actually.
Understood. Thank you. And last question, the fact that it can learn with so few samples and actually so much less information in terms of even input to the camera, does it mean that it's potentially less robust against potential noise in the input?
So I wouldn't say that it uses less data. So there's really no magic happening here. It's in this meta learning framework, like this one here. It's in the meta learning, so the offline learning stage, this network sees a lot of data. Really, I mean,
I understand. Yeah.
Okay. But then, so how robust is the resulting network? I think that remains to be seen. Like how robust would this network be if I change this task? Probably not very good, but probably better than a network that hasn't been trained before. I think the bottom line here is that we don't know yet, and it's possible that people have looked into this question of the generality of the meta learning approach, but whatever question that we ask there applies for the spiking network as well as to the conventional network. There's nothing special that we're doing here for the moment that would make that different.
Makes sense. Thank you.
Any other questions?
I have a question. So which task is more suitable for spiking neural network compared to the standard standard neural networks? And what kind of trade-off when we switching to spike neural network?
Okay, yeah, that's a great question. Let me answer. Did you have another question after that? Was that it? Okay.
No.
Okay, so that's a great question. I should have emphasized that a little bit more. So the spiking, in the same way that, let me just give you the general rationale. You wouldn't take a recurrent network to solve ImageNet, right? In the same way, you should not use a spiking neural network to solve ImageNet or do CFAR. Studies that do that, sometimes they do that, but it's really because we don't have a good benchmark available. Okay, so what this means is that we need to find tasks that work particularly well within the spiking neural network community framework. In this particular framework that I use, a spiking neural network is a recurrent neural network, so anything that has a dimension of time would be a good candidate. In general, the timing of, if you're familiar with recurrent neural networks, generally, your sequences are about, it can be about 100 units long, but the gradients are calculated across maybe 10 time steps. In this case, it's very different. We have one update of the recurrent network. Basically, I mean, if it were ideally, it would be a continuous update. But in the GPU, our simulations have a time step of 1 millisecond. So any task at this stage that requires to have that fine temporal representation would be a good candidate. I think, for example, an audio task or biomedical signal processing. Those signals are those where you can basically learn across where the fine temporal dynamics may play an important role. But the bottom line is a dynamical signal.
Thank you.
Other questions? So, so if no one want to ask question now, I would like to ask some questions. So Emre, your talk is very, very inspiring. So actually, I have 3 questions.
Oh wow! Okay, great.
And I think the first one is the spiking network for the deep network, and the rest 2 are the deep network for the spiking network. So the first one is that, so you mentioned that for the reverse and the forward modeling, and I remember you also mentioned that. So actually, those are the memory problem. That is, for example, we need to store those the intermediate results during the training, during the backpropagation. So that is not just a problem for the spiking network. So it is also existed for the deep network. So whether we can apply this approach to the memory efficient, the deep network training, it is possible.
Yes, actually, that's a really good idea, and it's already being done, right? So if you, for example, the Cerebras company has a very large chip, wafer scale chip, but they only have something like 18 gigabytes of memory. So how do they solve that problem? And they're using that for training. In fact, they use some techniques that also come from the auto differentiation field of, for example, checkpointing, where instead of retaining the entire graph, you only retain it at certain time points or certain level points, and then when you need the history, you regenerate it. It's also called regeneration.
Oh, okay.
So
okay.
that's one way to solve the problem, and you can have, in some cases, you can find an optimal checkpointing. So I think it's really, so that's really, I think, interesting work in itself, and it's probably going to play an important role in improving our training of learning in very large networks. I'm also very interested in what does checkpointing mean with respect to neural dynamics. It hasn't actually been studied that much at all, actually. And so there's some interesting pointers in the brain that, actually maybe these short replays, regenerations might actually be occurring. As for the forward AD, I don't think people use this in general in neural networks unless you really require that real-time aspect. But you're entirely right to say that everything that we're doing here has not much to do with, it's not specific to spiky neurons, which is, I think, a good thing, right? So we have this common framework in which we can use the same theories.
Okay, thank you. And my next 2 questions. First is that, so in your framework, you interpret the spiking network as kind of the type of the recurrent network, right? And I think that is kind of the standard recurrent network. And as we know that for the for those the classical recurrent neural work topology, so as compared to the its advanced variety like LSTM or the GRUs, typically suffers the vanishing gradient problem. So alone. So whether it also existed for the spiking neural work?
Oh yeah, that's a great question. Well, the LSTM was designed to prevent the vanishing gradient problem, and so in some sense, the spiking networks that we have here, they correspond to like vanilla recurrent neural networks without the fancy features of the LSTM. And they do have, of course, a vanishing gradients problem. In fact, just from this recurrence here, I mean, the signals G here or the F, they basically fade exponentially. So there's been some work actually in saying, well, if we can build a spiking neural network artificial recurrent neural network, maybe we can take some of the features of LSTMs there. And you can do that. In fact, there's the group of Wolfgang Maas and Graz did exactly this. So they introduce some internal dynamics to the neuron that are not exactly like the LSTM, but that really correspond to, that are closer to kind of biological dynamics in changing the threshold of the neuron. And it recovers the benefits of LSTMs and has better performance on long time horizon problems. Yeah, so that's exactly, that can exactly be done. And it's again, an open problem, like what neuron dynamics can we include here that would make that even better?
Okay, and so my third question actually is based on this. So if we think further, so right now, so in the NLP and in the speech, also even right now in the computer visions, the transformer, so adopting the attention mechanism right now, they try to even already outperform the recurrent neural work and even try to outperform this convolutional neural work. So whether this philosophy can be adopted into the design of the spiking neural work?
Yeah, that's a great question. I've been thinking a lot about transformers too. You know, I think the spiking neural networks are probably going to be good at learning at short time scales, so these very fine temporal time scales. But for the longer time scales, I mean, either use something like LSTMs or the transformers that kind of gate the information. I don't think there's no reason why you couldn't use spiking neural networks with transformers, and even if they have their time steps, that even if the signals are dynamic. I think we should just think of these, or the way I think of this for the moment, is at different time scales. So transformers are going to be great for learning across very large time scales because the information is already there. You don't have to, you won't have a vanishing gradient problem. But for learning these fine kind of temporal dynamics, I think the spiking time constants would be much more suitable. So we can use both together.
Thank you very much. I think that just like what you have done, what you are doing, the intersection between the conventional deep neural work and the spiking neural work is very, very interesting in the area.
Yeah, no, I think a lot of low-hanging fruits for sure. Yeah.
So any other questions from the audience? Okay, so if not, so thank you again, Emre. Very, very inspiring talk, and I learned a lot. Thank you.
Well, thank you, bro. Thanks all for your attention and for the invitation.
Thank you. Thank you all for attending our today's talk. Thank you.